and considering some of the likely questions we might encounter in 2024 JAMB. So let's start with the very first one. The equation, and this is the equation A, that's acceleration is equal to 2 plus 2t. Represent the acceleration of a particle in a time t. We have to find the instantaneous velocity after 4 seconds. Now, velocity can be gotten by integrating the acceleration. So that's integration of acceleration dt. And this is going to be integration of the acceleration that has been given as 2 plus 2t, then dt. And if we integrate this one, integration of any constant just carries that particular coefficient. So integration of 2 will give us 2t plus, if I'm integrating 2t here, that's going to be 2t raised to power 2 all over 2. Basically, this is what you have. If you have y is equal to x raised to power m. If you want to integrate this, integration of y here is same thing as integration of this. So if this one is integration, that's going to be dx. If you're integrating x raised to power n, that will give us x raised to power n. We had 1 here, that's plus 1. So whatever we have here, we also put it at the denominator here, n plus 1. So that's the way that is. So if you relate that with this, so that you're able to understand this, t is raised to power 1 here, even though 1 is not stated there. It's raised to power 1. That's going to be plus 1. So, and since this one is 1 plus 1, so whatever is up here, we also have it here. So that's going to be that. So 1 plus 1 here, that gives us 2. So which means 1 plus 1 here, we have 2 here. So 2 cancels 2. So we are left with v. Now is equal to 2t plus what? Plus 2 squared. That's all. And we have been given all the time 4 seconds. So which means our velocity now is equal to, anywhere we see t, now we put 4 there. So 2 times 4, then plus this one is 4 squared. That's going to be 2 times 4. That's going to be 8 plus 4 squared. That's 16. So if you add that together, that's meter per second. That gives us what? That's 24 meter per second. So it's as simple as that. So the correct option for this would be option C. So you can put this one down quickly. Let's put this one down very quickly so that you can look at the second question. And please write as fast as you can so that you can touch all the 20 questions. Let's go to the second question now. Let's take a look at what the second question says. The second question says a string with a force of 80 Newton. So that's the force. Force is equal to 80 Newton. Now, and extends a string with a force of, let's pay attention here. The string is acted upon by a force of 80 Newton, and that brought about an extension of 5 centimeters. So extension is equal to 5 centimeters. And we know this 5 centimeters cannot be left there. We have to convert it to meter. So that gives us 5 all over 100 meters. That's 0.05 meter. So always ensure that in question like this, you convert our centimeter to meter. Now, if the string is used to shoot a stone of mass 20 grams, so the mass of the stone is 20 grams. Not only that, this gram have to convert it to kilogram. That's going to be 20 divided by 1,000 kilograms. So here, we are left with 0.02 kg. That's also important. So, yes. Then what will be its velocity? Don't forget, when, for example, just like when you have a catapult and you want to use that particular catapult to actually throw a stone, when that particular stone is seen in that particular catapult, what kind of energy does it possess? Potential energy by virtue of its position. But once that particular string is extended and released, what happens? That particular stone leaves the catapult and begins to move with a particular velocity. So it now assumes what kind of energy? Kinetic energy. So which means that the energy that is stored in that particular string will have been converted to kinetic energy. Now, energy stored in the string. Energy stored in the string. And the string is equal to 1 all over 2 Fe. Or you can use 1 all over 2 Ke squared. Any one of it could be used. But we can simply make use of this one because we have been given the force, 80 Newton. We've been given the extension, which is this. So if you calculate the energy stored now, E now is 1 all over 2 times F. That's 80. Then times E. That is 0.05. Everything in joule. If you do this one, what does it give us? 1 over 2 times 80 times 0.05. What does it give us if you multiply them together? 4 joule, right? I just want someone who can be doing that and as fast and accurately as possible. That's 2 joule. So this 2 joule. Not only that, what will be the energy of the stone now? Energy of the stone. What kind of energy does it possess? Kinetic energy, which is half mv squared. So we know that this particular energy stored in the string will have been converted to the kinetic energy. So basically what we have is half Fe converted to half mv squared. And we know that half Fe, we've calculated that here, we've gotten 2 joule. So that's going to be 2 joule is equal to here 1 over 2 times the mass of the stone. We've calculated that to be this 0.02 times V squared. So that here we now have 2 is equal to this. We give us 0.01 times V squared because half of 0.02 give us 0.01. So here, what do? We can divide both sides by 0.01. 0.01. So which means our V squared now is equal to 200. Now if you want to calculate our V now can be square root of 200. Now 200 can be written as square root of 100 times square root of 2, isn't it? Using our sword. And what's square root of 100? That's right. That's going to be 10 times root 2. So that's going to be 10 root 2 meters per second. So, and if you take a look at the options, that's option A. So that's for that. Let's put that down very quickly. Let's speed down very quickly so that I can go to number 3. Okay, let's go to number 3 now. The third question. The surface speed of a vehicle on a curved horizontal road is that. Now, we know this is talking about when you see that particular curved horizontal road, it's talking about banking of the roads. Whenever you are traveling in a car and you approach a particular bend in that particular road, you notice that the road is always banked. You can actually see that at these corners, the roads are actually expanded more so that the car can actually move to the side, and the movement is always directed towards the center. You understand what that means? That's talking about the centripetal force or acceleration. Don't forget that the banking angle for any road tan theta is equal to v squared all over rg. Not only that, because the car is moving on a road, and don't forget, one of the things that actually ensures cars to move safely on a road and prevent it from skidding is friction. And we know that the frictional, the coefficient of kinetic friction tan theta is given by this. You see, remember this one from our friction, which we have done also. And if we equate the two of them together, tan theta is v squared all over rg, where theta is the banking angle, and tan theta is equal to the coefficient of this particular friction. If you equate the two of them, you are left with v squared all over rg is equal to the coefficient of friction here. So if you cross multiply both sides, then we are left with v squared is equal to this one multiplied by this gives us, right? And then we are looking for our v now. So which means that our v now is equal to square root of coefficient of friction rg. So that's what we need. And if you look at the option, that's definitely option B. As simple as that. That's okay. And please let's write as quickly as we can. Okay, let's go to number 4 now. The fourth question, it says, a small metal sphere of diameter 12 millimeter. So the diameter is 12 millimeter. So which means the radius is going to be diameter all over 2, which is going to be what? 6 millimeter. And if we are going to convert our millimeter to meter, we divide by 1000, that's 6. all over 1000, and that's going to be in meter, and that gives us 0.006 meter. So let's take note of that. That's the radius of that particular sphere. Is dropped into glycerin. Glycerin is a viscous liquid. If the viscous force on the object is 3.2, viscous force, that's F, is equal to 3.2 Newton. We have to calculate the coefficient of viscosity. This coefficient of viscosity, this is the sign. That's coefficient of viscosity. Coefficient of viscosity. And we are given that the object terminal velocity, which is V, is 8 meters per second. Now, we've done everything about viscosity before, and we remember that this is guided by what we refer to as the Stokes law or the Stokes equation. Stokes equation. And if you remember, that's F is equal to 6 pi R N V. F has been given. That's the viscous force. We know what pi is. That's the 3.14. We know what R is. That's the radius. We calculated it to be this. We know what V is. That's the terminal velocity will be given here. So what we need to simply do is we need to calculate the coefficient. This one. So we now say our coefficient of viscosity is equal to, that's F all over 6 pi what? R V. That's all. So which means F, that's 3.2 all over 6 times pi to 2 decimal place is 3.14 times R, the radius, 0.06 times, that's V, that's the terminal velocity, that is 8. So which means that coefficient of friction now is going to be 3.2 divided by, let's someone help us multiply this, 6 times 3.14 times 0.006 times 8. Everything multiplied. What do we have? 0.90432. So now if you divide that, what does it give us? 3 point what? 538. So that's 3.54. That's going to be Newton seconds per meter squared. So if you look at the option, what will be the correct answer now? Definitely option C, to 1 decimal place. That's going to be, the coefficient of friction now is 3.5 Newton seconds per meter squared. So the correct answer is option C. Let's put this one down very quickly. Okay, now let's move on to the 5th question. The 5th question says the charge carriers, not the change, please. The charge carrier, that's definitely a typographical mistake. The charge carriers in gases are A, ions, B, electrons, C, electrons and ions, and D, electrons and holes. The correct answer here is definitely option A. Now let me expatiate more. Now we know that different substances have different charge carriers. For example, the charge carriers in metals are mobile electrons only. The charge carriers in electrolytes are ions. The charge carriers in semiconductors like germanium, like silicon, are option D, which is electrons and holes. But the question is asking us, what are the charge carriers in gases? The only charge carriers in gases are the ions. That's the positive ion and the negative ion. So The correct answer once again for number 5 is A. Let's go to number 6. The force of attraction between two charges is 120 Newton. If the distance between the charges is doubled, the magnitude of the force will be that. Now, if you take a look at this, we notice that this is under electric field. Precisely, this is under what we refer to as the Coulomb's law. Remember, Coulomb's law is also called the inverse square law. Remember, Coulomb's law tells us that the force of attraction between two charges is inversely proportional to the scale of their distance apart. That's the most important thing here. So from this, F now is equal to K all over R squared, where K is constant. And if you constant apply, we are left with K now is equal to F R squared. So if you have from here, you can have F1 R1 squared is equal to F2 R2 squared. Or if you want to bring the force together, you can say F1 all over F2 is equal to what? That's R2 squared all over R1 squared. If you go and multiply, you're actually going to get this one back. So, which means is the initial force when the distance between the charges is R1. This is the final force when the distance between them is R2. But if we take a look at this question, we have been given F1. The initial force between the two charges is 120 Newton. Now, we are now being asked if the distance between the charges is double. So, if R1 is the initial distance, then if the distance is doubled, then R2 now becomes what? 2R1. That's the meaning. Because the distance is doubled. Doubled means multiplied by 2. So which means we are looking for what will be our F2. So let's rub this off and put it here. So not forgetting our formula, F1 all over F2 is equal to R2 squared all over R1 squared. So this will give us F1. We know that to be 120 all over F2. That's what we want to find out. We don't know. R2. Don't forget, R2 is 2R1. So that's 2R1. Everything what? Squared all over R1 squared. So this is now 120 all over F2 is equal to 2 squared. That's 4 R1 squared all over then here R1 squared. What do? We can constantly apply. So that here we now have F2 times 4 R1 squared is equal to 120 times R1 squared. R1 squared, we cancel R1 squared here. Then we are now left with 4 F2, that's 4 times F2 is equal to 120 Newton. And if you divide both sides by 4, then we are left with what? Our F2 is equal to what? 30 Newton, which is option B. So let's put that down. It's as simple as that. Don't forget, once again, this is what we refer to as inverse square law. And even if you remember, under gravitational field, Newton's law of universal gravitation is also another example of inverse square law. Let's put that down quickly. So don't forget, at times, instead of giving you values like this, they can actually ask the question in diverse way, in different ways. If you have charges, if you have two charges, let's say you have charges Q1 and Q2. Now the distance between them now is R. Whenever the distance between two charges is doubled, then the force of attraction between them is going to be reduced by a quarter. What's a quarter? divided by 4. So which means the original force between them is 120, but the final force now is 30. It has been reduced by what? By 4, because a quarter of 120 is 30. So the same thing, if you reduce the distance between them by half, that is, you bring them closer. When you reduce the distance between them by half, what happens? The force of attraction between them will be quadrupled. What does that mean, quadrupled? Increased by a factor of what? Of 4. That's that. So when the distance is doubled, the force of attraction is going to be reduced by a quarter. But when the distance between them is half, that's reduced by half, then the force of attraction between them is going to be quadrupled, multiplied by 4. That it increases 4-fold. So that's that. So what if you now triple it? If you triple the distance between them, what do you think will happen to the force of attraction between them? It will be due by what? By factor of what? Of 9. When you triple the distance, remember when you double it, the force of attraction between them decreases by what? By 4. That is, it is reduced by a quarter. But if you are now tripling, I mean, if you increase the distance by 3 times, then the force of attraction is going to reduce by 1 all over 9. So that's going to be 1 all over 9 multiplied by the original force. If the original force, for example, is, let's say, 180 Newton, if you triple the distance between them, then the final force now is now going to be 1 all over 9 multiplied by the original force, which is 180 Newton. Doubling the distance will reduce the force by a quarter. Tripling the distance will reduce the force by 9. That's 1 all over 9. Let's go to number 7 now. Number 7. It says the essential parts of an AC generator, that's alternating current generator, comprises the following, except. So the question is asking us, which of these components is not present in an AC generator? A, field magnet. Every generator, be it AC or DC, possesses field magnets. Option B, slip ring. AC generator possesses slip ring. Option D, brushes. It also possesses brushes. What it doesn't have is the split ring. Only a DC generator possesses split ring. Split ring is sometimes called commutator. So it's either you call it split ring or you call it a commutator. Commutator is only present in direct current generator. Direct current generator possesses split ring commutator or split ring or commutator, whereas an alternating current does not possess split ring commutator. So the correct answer here is option C. Let's go to number 8 rather. Now number 8 says a substance has a half-life. Let's clean this. A substance has a half-life of 5 minutes. After 10 minutes, the count rate was observed to be 500. What is its count rate at 0 times? Let's look up. Now, half-life, that's T half, will be given to be 5 minutes. And the time it takes it to decay, that's ordinary T, is 10 minutes. Now, the count rate was observed to be 500, so which means it has actually begun to decay. The count rate after 10 minutes, when it has started to decay, was observed to be 500. So that's N, 500. Then we are asked, what is the count rate at 0 time? That is when it is about to start decaying. That's N naught. Is unknown. Now, when you come across a question like this formula help us to solve it every single time. N all over L naught is equal to 1 all over 2 raised to power T, that's ordinary T, all over half-life, which is T half. This formula can take care of any question like this, anytime, any day. So N will be given to be 500, that's 500, all over N naught, that's the count rate at 0 time. That's what we need. N naught is equal to 1 all over 2 raised to power, what's our T? That's 10 minutes. Now 10 minutes divided by the half-life, which is 5. 10 divided by 5 gives us what? That's 2. So this gives us 500 all over n naught is equal to 1 raised to the power 2, that's 1. Then 2 raised to the power 2, that's 4. What do we do? Because of the plan, n naught times 1 still gives us n naught. 500 times 4, that gives us 2,000. So the count rate at 0 time is 2,000. And if you look at the option, that's option C. Let's put the solution down quickly. After that, we go to number 9. Okay, let's look at number 9 now. Number 9 says, calculate the maximum kinetic energy of liberated electrons when cesium of work function. First things first, work function is represented by W naught, that's our work function. I've been given the work function to be 2.5 times 10 to the power minus 18 joule. Is illuminated with light of frequency. So I've been given the frequency of the light, F, to be 8.6 times 10 to the power 15 hertz. Now remember, the formula for calculating the maximum kinetic energy, Ke max. Ke max is equal to E, that's the energy of the photon, minus W naught. This one can also be written as E is equal to HF minus W naught, that's HF naught. So we know what H is. It's a constant. Planck constant. H is always 6.6 times 10 power minus 34 joule seconds. And we have been given our F, which is this. So to calculate our E here is easy. So our E now is equal to HF, which is 6.6 times the power minus 34 times F. What's our F? 8.6 times 10 to the power 15. Let's find out what that gives us in joule. Let's someone do that for us very quickly. 6.6 times 10 to the power minus 34 times 8.6 times 10 to the power 15. What does that give us in standard form? That's 6.6. So that gives us 5.6. That's 5.676 times 10 raised to the power. That's times 10 to the power minus 18. Minus 18 joule. Now we know our E now. So remember, there is a formula we are using. So the maximum kinetic energy, Ke max, is equal to E. We just calculated our E to be this one, which is 5.676 times the power minus 18 joule minus W naught. That's the work function. We'll be given in the equation to be 2.5 times the power minus 18 joule. So let's subtract minus 2.5 times the power minus 18. So then our maximum kinetic energy now is 3.176 times 10 raised to the power what? Minus 18 joule. So if you look at this to two decimal places, Here, that's 3 point. Here, that's 2 times 10 to the power minus 18 joule. Which option is that? Option C. So it's as simple as that. Let's put this down very quickly. Let's go to the 10th question now. Number 10. It says the maximum kinetic energy of ejected photoelectrons depends on dash. Now, A, frequency of the photons, B, intensity of the light, C, speed of the light, and D, all of this. Now, the maximum kinetic energy of ejected photoelectrons depend on some things. The maximum kinetic energy of photoelectrons depends on a lot of factors. Number one, it depends on frequency of the light. At times, the light is also referred to as the what? As the photon. Not only that, it depends on the wavelength of the light. Wavelength of the light. Not only that, it depends on the color of the light. Color of the light. And finally, number 4, it depends on the nature of the photocathode. Now, let me explain this. The maximum kinetic energy of photoelectron depends on these 4 things. And the 4 of them, as a matter of fact, the very first 3 are actually interconnected because the color of the light, the frequency of a light actually depends on what color the light is. After all, we know under our dispersion of light in physics that red color has different frequency from violet color, isn't it? For example, red color has the fastest speed, isn't it? And the frequency is also fastest as what is highest. So the color of the light will determine what the frequency is. The color of the light will also determine what the wavelength is. And don't forget, frequency and wavelength are inverse of each other. The higher the frequency, the lower the wavelength, and vice versa. So any light that have high frequency will have low wavelength or short wavelength. So to answer the question from the extension I've given here, you can see that the correct option is A. So the maximum kinetic energy of ejected photoelectrons depends on A, which is frequency of the photon. Now, it is possible at times that you can be asked, they can ask you that the number of photoelectrons will depend on that. Now, the question is no longer asking about the maximum kinetic energy, that is, how many photoelectrons will be ejected when light is incident on a particular photocathode. The number of photoelectrons ejected depends on option B, that is the intensity of the light. The higher the intensity, the more the number of ejected photoelectrons. The lower the intensity, the lower the number of ejected photoelectrons. So let's take note of that. For the maximum kinetic energy, it depends on frequency of the photons or light. Then the number of ejected photoelectrons will depend on what? On the intensity of the light. So that's option A. Let's go to number 11. Let's clean this. Let's clean that part. Okay, so number 11 says, find the charge on a stationary oil drop of mass 500 grams. So first things first, the mass is 500 grams. What are you supposed to do here? Convert from gram to kilogram by dividing by 1000. So this will give us 0.5 kilogram. That's the very first thing. Located at a distance 5 millimeters. So distance B is 5 millimeters. Can we make use of the 5 millimeters? No. We have to convert to meter. So that's going to be 5 all over 1000 meters. That gives us what? 0.005 meters. Now, between two plates with a potential difference of 1 kilovolt. So potential difference, PB, is equal to V, which is 1 kilovolt. Which is same thing as what? 1000 volts. So we are given our acceleration due to gravity to be 10 meters per second squared. Now, remember that there is something called electric field intensity, because any charge experiences that particular intensity. For example, electric field intensity E, electric field intensity, actually has two formulas. It's either you say E is equal to what? F all over Q, which is the charge. We all know that electric field intensity is the ratio of the force to that particular charge. Not only that, electric field intensity is also equal to the potential difference V. That's potential difference all over the distance, which is going to be V all over D. As a matter of fact, there are two units of potential difference of electric field intensity, and from those two units, you know what the formulas are. One of the units of electric field intensity is Newton per Coulomb. Look at that, Newton per Coulomb. What does Newton represent? That's force. What's the meaning of per Coulomb? That's 1 all over what? Charge. So that's force all over charge. Another unit of electric field intensity is volt per meter. What does that mean? Volt, that's the potential difference. Per meter is something as 1 all over the distance. So you can see. So if you now equate this one, if you equate this one and this, let's see what we get here. So that's going to be F over Q. So that's F all over Q is equal to air. That's V all over D. But don't forget, this one is force. And if you remember, we know that our force is mass times acceleration due to gravity. We still remember that, right? So if you substitute that with F here, we're now left with mg all over, that's our force, all over Q now, is equal to V all over D. That's V all over D. What do? We cross multiply. So now have Q times V, that's QV, is equal to mg times D, that's mgd. Don't forget, what did the question ask us to calculate? The charge, which is our Q here. So if you divide both sides by V, now, then our charge Q now is mgd all over V. So finally, we can now see our charge now is M. That's the mass, 0.5 times our acceleration with gravity, we have been given to be 10 meters per second squared, times our D, the distance between them, we calculated it to be this, 0.005 all over, then our voltage, potential difference, that's 1000. 1000. Everything in Coulomb, because that is the unit of our charge. That's 0.5 times 10 times 0.005, then divided by 1000. So finally, it gives us 2.5 times 10 to the power minus 5 Coulomb. Which option is that? That's option C. And don't forget, Option C is different from option D because this one is 2.5 times 10 to the power minus 5, and option D is 2.5 times 10 to the power ordinary 5. That's different. So the correct answer here is option C. Let's put the solution down quickly. Then we shift our attention to number 12. Let's put them very quickly. Okay, so let's shift our attention to number 12. It says, what is the Broglie? Sorry for the typographical mistake. That's the Broglie, the DE. Broglie should be spelled as Brogle. So what is the Broglie wavelength for an electron moving with a speed of, now the speed of the electron, V, is 3 times 10 to the power what? Times the power what? Times the power minus 6 meters per second. But don't forget, we also need the mass of electron, which is also the constant. What is the mass of an electron? 9.1 times 10 to the power minus 31 kilogram. It's a constant. And you might or you might not be given during the exam. So it is very important for you as students to be able to know what those constants are. The Planck constant, 6.6 times 10 to the power minus 34 joule seconds. The mass of electron, 9.1 times 10 to the power minus 31, because you can be given at times, you might not be given. So you have to know that. And according to the Broglie expression, we know lambda, that's the wavelength, is equal to h all over mv. H is the Planck constant, which is 6.6 times the power minus 34 all over the mass of the electron. That's this, 9.1 times the power minus 31 times the velocity of the electron will be given to be 3 times 10 to the power minus 6. So lambda now will give us this, that's 6.6 times the power minus 34. Now, if we multiply this, that's 9.1 times 10 to the power minus 31 multiplied by 3 times 10 to the power minus 6. Then that gives us 2.73 times 10 to the power what? Minus 36. And then if you divide now, don't forget the unit of this is going to be meter. So that's 6.6 times 10 to the power minus 34 divided by 2.73 times 10 to the power minus 36. And that gives us what? 2.42 times the power what? 2.42 times 10 raised to the power what? Times the power what? 2.42. I assume you are doing it as I am. 2.42 times the power what? Minus. Check it out. Times the power minus what? Just divide 6.6 times the power minus 34. Then you divide it by 2.73 times the power minus 36. That's 6.6 . So that gives us times 10 to the power 2 actually. 2.42 times 10 raised to power 2. If you do it very well, that's going to be in meter. So if you look at the option, none of that is correct. None of the options. Because even looking at this, you know this one is going to be taken up here. So it becomes minus 34. By the time this one comes up, it becomes plus 36. That will give you what? 2. You should know. That's what we are going to have there. So the correct answer here is 2.42 times 10 to the power 2 meter. None of the options is correct because option A is 2.4 times 10 to the power minus 10. Option B, 6.2 times 10 to the power minus 15. C, 3 times 10 to the power 8. And D, 2.5 times 10 to the power 16 meters. So none of that is correct. This is the correct answer. Let's put this one down quickly. And please remember, this is the Broglie equation because at times they even ask this expression. They can ask you which of the following expressions represent the Broglie equation. It is lambda is equal to h all over mv. Although at times it can also be expressed as lambda is equal to h all over p. What does p represent? Momentum. Because you know that the product of the mass of a substance times the velocity is what? It's momentum. So it is either lambda is equal to h all over mv or lambda is equal to h all over p, where p is momentum. So let's take note of that. Let's be done very quickly. And I think I know where the problem is. Now, if you make use of this, I think that's where the problem is. Maybe the question, at least the question, if this is 3 times 10 to the power 6 instead of 3 times 10 to the power minus 6, then the answer you'll be getting will be this. Let me show you what I mean. Remember, the speed is 3 times 10 to the power minus 6. If it were to be v is equal to 3 times 10 raised to the power 6, that's positive meter to minus meter per second, and ME is still the same thing as 9.1 times the power minus 31 kilogram, and we know our H is 6.6 times the power minus 34 joule seconds. Then our lambda would be H all over MEV, which would be H 6.6 times the power minus 34 all over M 9.1 times the power minus 31 times V 3 times 10 to the power 6. Now what we are going to have now is 6.6, which is this, times the power minus 34 all over. If you multiply this, you are getting 2.73 times the power minus what? 24. Now if you divide this and with this, now tell me what will be the answer? Divide this and this. 2 point what? 4 times by what? Minus 10. So I think that's where the problem came from. It should have been plus 6, not minus 6. But what we did earlier, if you leave it at minus 6, the answer we got originally is the correct one. But if You change this minus 6 to plus 6, then the correct answer will actually be there. And as you can see from what we've done here, the answer will have been option A, which is 2.4 times 10 raised to the power minus 10 meter. It doesn't matter what the values are. What matters is for you to know what formula to use and what step to take in arriving at that answer. Okay, now let's look at number 13. Number 13 says, in a nuclear fusion experiment, that's in radioactivity, a mass defect of 0.05 AMU. And in case you don't know, AMU stands for atomic mass unit. So the mass defect, remember mass defect is written as delta M is equal to 0.05 AMU. Don't forget, we have been given what is 1 AMU? 1 AMU is 1.6 times 10 power minus 27. So which means this one is the same thing as 0.05 times what? 1.67 times 10 power minus 27 kilogram. What will that give us now? If you multiply that, 0.05 times 1.67 times 10 to the power minus 27, that will give us 8.35 times 10 to the power minus 29. Minus 29 what? That's kilogram. I will be given the speed of light now is 3 times 10 to the power 8 meters per second. And we know that the energy E is equal to what? Delta MC squared. We still remember that famous formula? And then we know our delta M now to be this one. So that's 8.35 times 10 to the power minus 29 times C squared, which is this one. That's 3 times 10 to the power 8 all squared. Everything in joule. So this becomes 8.35 times 10 to the power minus 29 times this one square will give us 9 times 10 to the power what? 16 joule. 3 squared, that's 9. Then 8 times 2, that's 16. And then if you multiply everything together now, that's going to be times 9 times 10 to the power 16. That's going to be 7.515 times 10 to the power what? That's minus 12 joule. So, and if you look at the options, that will definitely be option B because to one decimal place here, 7.5 times 10 to the power minus 12 joule. So let's put that down. And please don't forget, at times, you can be given the mass defect in gram. When you're given the mass defect in gram, the very first thing you should do is to convert from gram to kilogram. On no occasion should you use that particular gram alone without converting it to kilogram. Let's put that down quickly. Then we move on to number 14 when you are done. Let's do that quickly so that I can go to the 14th question. Okay, let's go to number 14. It says a material has a work function of 5 eV. The full meaning of eV is electron volts. Work function, I've told you work function is W naught. Work function. And we are given 5 electron volts. And by the way, even I've seen JAMB question asking you the unit of electron volt is dash. That's joule. Electron volt is measured at the same unit as work done. So please take note of that. The unit of electron volt is joule. The same thing with work. And don't forget, 1 electron volt, that's one of those constants I asked you to take note of. 1 electron volt, you can see the question weren't given. But as a good student of physics, you have to know that 1 electron volt is equal to 1.6 times 10 to the power minus 19 joule. Because after I told you, the unit of electron volt is joule. So what do we do now? We convert this one to joule. So that 5 electron volt now become 5 times what? That's 1.6 times 10 to the power minus 19 joule. Let's find out. What will that give us? 1.6 times 10 to the power minus 19 joule times 5. That gives us 8 times 10 to the power minus 19 joule. That's 8 times 10 to the power minus 19 joule. But don't forget that work function W naught, from what we've done before, is equal to H F naught. What is our H? Another constant called Planck's constant. And what's our F naught? That's the threshold frequency. That's even what the question is asking us to calculate. So our F naught is equal to what? That's our W naught. That's the work function all over what? The Planck constant H. And the work function is calculated to be this one. That's 8 times 10 to the power minus 19 all over the Planck constant, always 6.6 times 10 to the power minus 34. And the unit of frequency is hertz. So our threshold frequency now is going to be 8 times 10 to the power minus 19 divided by 6.6 times 10 to the power minus 34. And if you do that, we are getting 1.21 times 10 raised to the power what? Times 10 to the power 15 hertz. And if you look at the options, which option is the correct one? Option B. So our F naught now is 1.2 times 10 to the power 15 hertz. So that's that. Now, before we leave this question, I think it's important I let you know what work function is. Now, if you want to define work function is the minimum amount of energy required to eject electron from the surface of a metal. Remember, during photoelectric effect, when light of adequate frequency is incident on a particular metallic surface like cesium, electrons will be ejected from that particular surface. We call those electrons photoelectrons, isn't it? But the amount of energy, the minimum amount of energy that is required to eject electrons from the surface of a metal is called work function. What does that mean? It means that if the work function, for example, look at this question. It says a material has a work function of 5 electron volts. So which means that the minimum amount of energy that can eject electron from the surface of this material is 5 electron volts, or 8 times 10 raised by minus 19 joule. If you now apply an energy that is, say, 3 electron volt, which is less than that particular work function, what will happen? Nothing. No electrons will be ejected. Before electron can be ejected from the surface of a metal, the energy supplied must be equal to or greater than the work function. That's why it is the minimum amount of energy that is required to eject electron from the surface of a metal. So if the work function is 5 electron volt, and you're now applying an energy of 3 electron volt, no electrons will be ejected. But if the work function is 5 electron volt and you apply an energy of 7 electron volt, definitely that is higher than the work function, so it will eject electrons. So take note of that. Not only that, threshold frequency is the minimum frequency that is needed to eject electron from the surface of a metal. And the same thing, if the threshold frequency is this, for example, 1.2 times 10 to the power 15 hertz, any frequency less than this will not be able to eject electrons from the surface of such a metal. So a light of this frequency can eject electron from the surface of this metal, but any light of frequency lesser than this will not be able to eject electron from the surface of a metal. So in a simple term, work function is the minimum, the lowest amount of energy that is required to eject electron, to remove electron from the surface of a metal. When you have energy equal to or greater than the work function, then electrons will be ejected. But when you supply an energy lesser than the work function, no electrons will be ejected. So please, let's take note of that. Okay, so let's look at number 15. Number 15 says, when an atom is in an excited state, it means A, electrons have moved to higher energy level. B, electrons have increased. C, potential energy is maximum. And D, protons have increased. When you see the word excited state or excitation, even by definition, excitation is the process whereby an electron absorbs or gains energy and moves from a lower energy level to a higher energy level. From that explanation, the correct answer will be what? Option A. So when you say an electron, an atom is in an excited state, it means that the electrons have moved from a lower energy level to a higher energy level. For example, if you have this one at the lowest energy level, that's E0, and this as having E1, that's a higher energy level, and this E2, that's also a higher energy level. So if an electron is initially at this particular ground state, when the electron absorbs energy, what happens is going to jump from the low energy level and go to a higher energy level. You say it has undergone excitation. So excitation, simply put, is the process whereby an electron absorbs energy. The energy absorbed can be in form of light, and therefore moves from a lower energy level to a higher energy level. And don't forget, that particular electron that is initially at the ground state and absorbs energy and becomes excited by moving to a higher energy level, it can remain at a higher energy level for life. After some time, what happens? It will lose the energy that it initially gained. And when it does that, what happens? It will return to the ground state or to that particular lower energy level that it was before it moved to a higher energy level. So the correct answer for that is A. Number 16 now. The maximum kinetic energy of emitted electrons in a photocell can be increased by, the good thing about this question is I've explained what kinetic energy, what it depends on earlier, isn't it? In our previous question today, we encountered a question that was asking us, what factor does the maximum kinetic energy of ejected photoelectron depend on? And I gave you 4 factors that it depended on. If you've forgotten, it depended on the frequency of the photon, isn't it? The color of that particular light, the wavelength of that particular light, and the nature of the photocathode. Now, let's focus on the 2 important ones there, which is the frequency of the photon or light and the wavelength. When I was explaining that, I told you that frequency and wavelength are inversely proportional to one another. Even you remember from your knowledge of physics, you know that V is equal to F lambda. V is the speed. F is the frequency, lambda is the wavelength. So if you make F here the size of the formula, what are you going to have? V, that's equal to all over lambda. What does that mean? It means that F is inversely proportional to what? To the lambda. So which means that as frequency increases, the wavelength decreases. That's what I meant the other time, that any light of high frequency will have short wavelength and vice versa. So the higher the frequency, the shorter the wavelength. And if you want to get maximum kinetic energy, what do you need to do? You need to increase the frequency. And if you look at the options here, was there any mention of frequency? No. But we can use that because we know that the higher the frequency, the higher the maximum kinetic energy. And we know that the higher the frequency, what happens to the wavelength? The lower the wavelength. So if you want to achieve a maximum, or if you want to increase the maximum kinetic energy, what do we need to do? We have to reduce or decrease the wavelength. So look at option A, increasing the wavelength. That's wrong. Option B, which is the correct answer, decreasing the wavelength. Now, there are two ways of increasing the maximum kinetic energy of emitted electron. Number one, by increasing the frequency, but there is nothing like frequency in the option here. And you know that as you are increasing the frequency, you are decreasing or reducing the wavelength. So it's either you increase the maximum kinetic energy of electrons by increasing the frequency, or by decreasing or reducing the wavelength. So the correct answer for this is option B. Let's go to number 17. Now number 17 says, let's clean the board first. So number 17 says, when an alternating current is given by I, that's the current, is equal to 10 sine 120 pi t, and that particular current passes through a resistor of 12 ohms. So which means R is equal to 12 ohms. Then we are asked to calculate the power dissipated in the resistor. Don't forget, the power dissipated, P, is equal to what? I squared R. We all know that. But don't forget, what is particular I here? That's the root mean square value, isn't it? And don't forget that root mean square value. The root mean square value is the peak value all over square root of 2. Do we still remember that? And if you look at this equation here, what's the peak value? That's 10. Because this equation can be compared with this. I is equal to I naught sine WT. Isn't it? Don't forget this particular one here is same thing as 2 pi f. I hope you still remember. That's right. So if you compare this equation with this equation, you can see that I naught here, which is the peak value of current, is equal to 10. So if you want to make this our formula now, it means that our P now is equal to, what is our I? That's the root mean square value. That's I naught all over root 2. What's our I naught? That's 10. So that's 10 all over root 2. All what? All what? All squared times, what's our R? I'll be given, that's 12. And the unit of work done is watt. Then 10 squared, that's 100 all over. Now, square of root 2, the square will just remove that particular square root. I hope you know that. So then times 12 now. So this one is here, 1, here, that's 6. What's this at 100? So P now is equal to 600 watts. As simple as that. Please, before you write anything down, let's look up. If you are not careful, you will simply make use of this particular 10 here, and the answer will be wrong. And guess what? You're going to see exactly the wrong answer that you got. If you make use of your 10 directly, that's going to be 10 squared times R. What 10 squared? 100. What's 100 times R? R is what? Is 12. What's 100 times 12? 1000 what? 1200. You can see that as option A. So that's it. So you have to be very, very careful, because the current here is not the peak current. It is the root mean square value current, which is the peak value divided by root 2. Be very careful of that. Let's put this one down. Then we go to the 18th question when you are done. Kuro, brother. Let's be done very quickly so I can go to the 18th question. Okay, now let's look at the 18th question. What did he say? He said two inductors of inductances 4 Henry. Don't forget, the unit of inductance is what? Is Henry. What the unit of reactance? The unit of reactance? Ohms. Remember, what the unit of resistance is ohms. The unit of resistance is the same thing as the unit of reactance is also ohms. The same thing, the unit of impedance is also ohms. So resistance, inductance, impedance, they all have the same unit, which is ohms. But the unit of inductance is Henry, capital letter H, Henry. So it says two inductors of inductances 4 Henry and 8 Henry are arranged in parallel and a current of 10 ampere. So the current passing through is 10 ampere. We have our L1 to be 4 Henry, and we have our L2 to be 8 Henry. Now, we are told they are arranged what? In parallel. And you have to calculate the effective or the total inductance. And the same thing as resistance. All right? If you want to calculate the sum or the total resistance that are connected in parallel, what do? It's just like this. Just like when you have this, that's all. That's the way it is. So if this one is L1, that's the first inductor, and this one is L2. So if you want to calculate the total inductor now, that's going to be 1 all over L total, that's LT, is equal to 1 all over L1 plus 1 all over L2. So that's going to be 1 all over L total is equal to 1 all over, what our L1, that's 4, plus 1 all over our L2, that's 8. And the LCM of 4 and 8, that's 8. 4 goes in 8, 2. 2 times 1, that's 2, plus 8 goes in 8, 1. 1 times 1, that's 1. So which means 1 all over LT is equal to what? 3 all over 8. And if you cross multiply, then we are left with 3 LT, because that's 3 times LT is equal to 1 times 8. That's going to be 8. What does that tell us? It means that the total inductance now is going to be what? 8 all over 3 Henry. That's all you need. And then what are we asked to calculate? The energy stored in an inductor. So this is the formula. Energy stored in an inductor is equal to 1 all over 2 Li squared. That's all. Let's look up now. That's 1 all over 2 times, what's our L? We calculate it to be this one, 8 over 3. That's 8 all over 3 times, what's our current? That's 10. So 10 squared is what? 100 over 1. So here, that's going to be 4. 4 times 100, that's 400 divided by what? Divided by 3. That's joule. Oh, that gave us 400 divided by 3. Yes? Anybody? 133 point what? Okay, so 133.3 joule. And if you look at the option now, what is the correct option? That's definitely option A. So that's that. Don't forget, that's the formula for calculating the energy stored in an inductor, half Li squared, where L is the inductor or the sum or the total inductor, and I is the current. And don't forget, this particular current can sometimes be given in milliampere. If you are given a milliampere, what do? You divide by 1000 and convert it from milliampere to ampere. On no occasion do you use that particular current if it is in milliampere. It has to be used only when it is in ampere. Let's put that down. Then when you are done, we go to the penultimate question, the second to the last question. Let's hurry up so you can go to number 19 when you are done writing the solution. Okay, let's look at number 19, the second to the last one. Which of the following is not an application of eddy current? Let's stop there. Just ignore that question for a bit. What do we understand by eddy current? Because if you don't know what eddy current is, there is definitely no way of knowing what the application is. Now, eddy current is always produced. At times, it is called induced current. All right. And even you remember the particular law, we call it Lenz's law. We remember Lenz's law, right? Lenz's law. I want to believe you still remember this one. It is Lenz's law that gives the direction of induced or eddy current. And don't forget, in JAMB, instead of eddy current, it can also be called Foucault's current. Yeah, attention to that. Instead of call it eddy current, that's another name for it. The particular science is called Foucault. So eddy current, Foucault current, we're talking about the same thing. And Lenz's law gives us the direction of induced current. I told you induced current is also called eddy current or induced EMF. What did he say? Lenz's law tells us that the direction of induced current or induced EMF is always in a way to oppose the change producing it. And not only that, even in JAMB, they ask you this a lot, that Lenz's law is a conservation of that. Conservation of what? Of energy. Please take note of that. Lenz's law is always a conservation of energy. You might want to jot that down so that we're going to go back to the question in a bit. I just want you to know what eddy current or Foucault's current are. These are the currents that always move in the opposite direction to the change or to the motion producing them. And the direction of eddy current or induced EMF is always given by Lenz's law, which works on the principle of conservation of energy. Now that we've established that, one thing you need to know about eddy current is this. Eddy current has both advantages and disadvantages. Now, one of the disadvantages of eddy current is they produce unnecessary heat. They bring about heating, intense heating in a particular appliance. And if the heating is too much, it can destroy the insulation of that particular machine. Not only that, it also leads to wastage of power. Anything that produces unnecessary heat will also lead to wastage of power. But does it mean that it doesn't have any advantage? It surely does have advantages. Number one, eddy current is applied in the speedometer in cars. That's one of the applications of eddy current. It is applied in the speedometers of cars. Not only that, all these I trains, we don't have I trains here in Nigeria, for example, but if you go to other parts of the world, the US, China, and so on and so forth, you have all these high-speed trains. They don't make use of the normal braking mechanism that we have, the kind of brake we have in cars. It is eddy current that is used in the braking system of fast speed or high speed trains. So you can see, even if you're looking at the board, you can see the speedometer is one of the applications of eddy current. Braking system of high speed train is also one of the applications of eddy current. Not only that, if you're looking at induction coil, that is also one of the applications of eddy current. The only one out of the four options that is not an application of eddy current is detection of cracks in railway tracks. So the correct option for this is option A. So let's take note of this. Let's go to the last question now. Number 20. Let's connect the board first. Okay, now let's look at the last question. It says a galvanometer with a full-scale deflection of 10 milliampere. That was what I was talking about some time, like some moments ago. You are given the current here in milliampere. So current I is equal to 10 milliampere. What are we supposed to do? We divide by 1,000 to convert it to ampere. Divided by 1,000 ampere to here, that gives us 0.01 ampere. Now, it will be converted to a voltmeter of full-scale deflection 5V. So the PD is equal to V, which is 5 volts. If a series resistance of 498, so series resistance R is 498 ohms, is used for the conversion, then the resistance of the galvanometer is dash. Resistance of the galvanometer we always represented by RG. Resistance of the galvanometer, we don't know what that is. Before we look at this, let's look up. Now, galvanometer is an instrument that can be used, among other things, to detect or to measure small amount of current. But galvanometer can be converted to an ammeter. It can also be converted to a voltmeter. If you want to convert galvanometer to an ammeter, we are going to connect a low resistance called a shunt, S-H-U-N-T, in parallel with it. Let me say that again. A galvanometer can be converted to an ammeter by connecting a low resistance called a shunt in parallel with it. On the other hand, if you want to convert a galvanometer to a voltmeter, what do? You connect a high resistance in series with it. That particular high resistance you are connecting in series is called a multiplier. Don't forget, when you are converting your galvanometer to an ammeter, what kind of resistance you connecting in parallel with it? Low resistance. And that low resistance that is connected in parallel with it is called a shunt. But when you are converting your galvanometer to a voltmeter, what kind of resistance are you collecting? High resistance. In what? Is it parallel or series? In series with it. And that high resistance that is connected to a galvanometer in series to convert it to a voltmeter is called a multiplier. And the formula is this. Simply V is equal to I into RG plus R. That's all. V is the full-scale deflection. That particular potential difference. I is the current passing through it. ROG is the resistance of the galvanometer, and then R here is the shunt, that particular high resistance. So we give our V, which is 5. We know our I, which is 0.01, is equal to ROG. That's what we are looking for. Then plus R, we have been given the multiplier 498. What do? We can divide both sides by 0.01. What's 5 divided by 0.01? 500, right? That's 500 is equal to, so this will cancel it. So we are left with ROG plus 498. What happens? We bring this one to this side. So that we now have 500 minus 498 is equal to RG. That will give us what? That's 2 ohms is equal to RG. So the resistance of the galvanometer is now equal to what? That's 2 ohms. So as simple as that. So that's for that. So we've come to the end of the questions. Thank you.